Today we're going to discuss this interesting problem that asks about what possibilities there are for the determinant of a matrix if it has specific types of entries. So given a 4x4 matrix A, where each entry of A is either 1 or -1, the question is, what are the possible values of the determinant of A? Okay, so let's write out A as some kind of matrix. So we'll have something like A11, A2, or I guess we already have things written in terms of capital A, so let's do that. So we'll have something like A11, and so it looks something like this. All right, so that's pretty great, and we know all these entries are 1 or -1. So one thing that we can do is let's take like the second row and subtract the first row, right? So we'll replace the second row by the second row minus the first row. Okay, so if we do that row operation, it doesn't change the determinant. But let's think about the entries that will be in the second row now. So the entries in the second row were either 1 or -1 to start with, and then we're subtracting 1 or -1 to end with. So we have a situation that looks something like this. We're either subtracting 1 from a -1, or subtracting 1 from a 1, or adding a 1, because we're subtracting a -1. Maybe I'll write that down that way. Subtracting a -1 from either of these. So we're either going to be left with a -2 or a 0 or a 2 in the entry. So if we do that to every one of these subsequent rows, where we replace, say, row 3 by row 3 minus row 1, and row 4 by row 4 minus row 1, then the entries in these 3 rows now, after that row operation, will live in the set -2, 0, and 2. Okay, so what does that mean as a consequence? Well, that means that each of the entries of this row is a multiple of 2, and the same thing with here, and the same thing with here. So we can factor out that 2 from each of these 3 rows, and we'll end up with a matrix that has as its entries positive or negative 1s and 0s, and then a factor of 2 to the third outside, if we're looking at the determinant, right? And so the determinant of A is 2 to the third times the determinant of some matrix that looks like this, right? And the reason is we factored out a 2 from each of the second, third, and fourth column, and factoring out a 2 multiplies the determinant by 2. Okay, now this thing here is going to be an integer because all of its entries are integer. So this thing is going to be a multiple of 8. So let's at least record that as one of the things that we do know, that the determinant of A is going to have 8 as a factor. I'll write that a little bit cleanly. So 8 divides the determinant of A. And we know that the determinant of A is actually an integer because its entries are all integer. So now we know that it has to be actually a multiple of 8. All right, so that's a great start to getting us off somewhere. All right, so now that we know that the determinant of A is a multiple of 8, we know it's either like 0, 8, 16, 24, or the negatives of those. What we'll do is play around with the actual matrix itself to see if we can bound the size of the determinant. So I'm going to let D be the determinant of A just for simplicity. So D itself is, we can expand along the first row. It's going to be A11 times the determinant of, we're going to write this down as little a11. So this thing here, in general, Aij, I'm going to denote as the determinant of the matrix where we get rid of the ith row and the jth column, and just keep all of this stuff. So this is the ijth minor. Okay, so this is this, and then we're going to add a12 dot a12 and a13 dot a13, and then a14 dot a14. Okay, so if we're trying to bound the size of D, an absolute value is going to be less than or equal to by the absolute value of all of the sum of all of these, which is going to be less than or equal to the absolute value of all of these things, added up by the triangle inequality. Okay, and the absolute value of the AIIs are all 1 because they're all positive or negative 1. So this is 1, this is 1, this is 1, this is 1. And so we can effectively erase their contributions. They're being multiplied by, or they are positive or negative 1. So I'll get rid of that. And say we have something like this as an upper bound on the absolute value, the determinant. And all of these added up. Okay, so what can we do with this? Well, now these are the determinants of 3 by 3 matrices, all of whose entries are positive or negative 1. And so we can bound the absolute value of each of these. Okay, and so we're interested in bounding the determinant of these 3 by 3 minors. Okay, so we can kind of use a similar idea as we did before. So by the same argument that we had, that in a 4 by 4 matrix whose entries are positive or negative 1, that 8 divides the determinant of A, we're going to know here that actually 4 divides the determinant of this. And it's the same idea where we have this 3 by 3 matrix. The second row, we can subtract the first row, and in the third row, we can subtract the third row. And so the second row and third row are going to end up with 2's and negative 2's and 0's in their entries. We can factor out the factor of 2 to get a factor in each to get a factor of 4 in the determinant. Okay, on the other hand, if you look at the determinant of Aij, by a cofactor expansion, actually I'll look at a specific one just to make things concrete. Let's look at the determinant of A11. Okay, so that's this block right over here. And so it is A22 times the determinant of some 2 by 2 matrix plus A33 times the determinant of some 3 by 3 matrix, and then A44 times the determinant of some other 2 by 2 matrix. Okay, and again, if we look at the absolute value of this thing, it's going to be less than or equal to the sum of the absolute values of all of these things. These all have absolute value 1, and so it's less than or equal to the sum of the absolute values of these 2 by 2 determinants. Okay, how big can these 2 by 2 determinants be? So the entries are 1 and negative 1. So we'll have something like maybe a matrix like this, or a matrix like this, etc. And there aren't many matrices to check. So first of all, this matrix here has determinant 0, and so does this one. Okay, then you have a matrix like this, whose determinant is 1 minus negative 1, so that's 2. And then you have the negative of it. And you can kind of see how this goes on. And it turns out, no matter what, that the determinant is going to be at most in absolute value 2. You can't get anything larger than that. You can kind of see that actually explicitly. So if you had a 2 by 2 matrix A, B, C, D, its determinant is AD minus BC, right? And so the absolute value of AD minus BC is less than or equal to the absolute value of AD plus the absolute value of BC. And both AD and BC are positive or negative 1 because AB and DC themselves are all positive or negative 1. So this is at most 2. Okay, so then as a consequence, all of these things here are bounded above by 2. And so the determinant of A1 is actually bounded above by 6, but in absolute value. But 4 is a factor of the determinant of A11. And so that means that the determinant of A11 itself has to either be 0, 4, or negative 4. And so its absolute value is at most 4. And so if you go back up to the bound on the absolute value of the determinant of A, all of these things right here are going to be bounded above by 4 by these calculations we just did below. And so in total, the absolute value of D is going to be bounded above by 16. Okay, great. But the determinant of A, which is what D is a multiple of 8 and is an integer. So if it's bounded above by 16, that tells us that there aren't many choices for what the determinant of A can be. The determinant of A then has to live inside of the set negative 16, negative 8, 0, 8, and 16. Okay, so we've reduced the number of choices down dramatically, and now the question is, can we actually achieve all of these values, or do we need to restrict more, and are some of these values not possible? All right, so let's take some time to think about that. Okay, so we can knock out one of these cases actually somewhat quickly, which is the 0 case. So we need to make a 4x4 matrix that's not invertible, that has entries that are positive or negative 1. We can do that by making the matrix have, say, all 1s as entries. Then this matrix is not invertible because it has repeated rows. And so the determinant of this matrix is 0. And so we've established that 0 is a possibility. Now the question is what happens with this 8 and 16 and negative 16 and negative 8. So if we can achieve one of these values, 8 or 16, or negative 8 or negative 16, then by multiplying one of the rows by negative 1, we can achieve another value. So for example, let's say we had a matrix whose determinant was 8, then we should be able to find a matrix whose determinant is negative 8 by multiplying the first row by negative 1 all throughout. Okay, so it's not really easy to construct a matrix that has a pre-described determinant, but there's something that we can do that's actually motivated by a different video on this channel. And the idea is using what's called the matrix determinant lemma. Okay, so I'll state two different versions of it because both of them will actually end up being kind of useful here. So the first version I'll state, which I'll use directly, is the following. So let's say you have a matrix A, and you have two vectors, u and v. So A, I'll make just A a 4x4 matrix because we're in 4x4 land. So A is 4x4, and u and v are both in Rn, or R4. Okay, then this lemma states that if you take A and perturb it by uv transpose is a 4x4 matrix, that this thing is going to turn out to be the determinant of A times the scalar 1 plus v transpose A inverse u. Okay, so how is something like that helpful? Well, you can start off by constructing a matrix that looks like this. You have negative 1s in diagonal and 1s everywhere else. And so why would you do this? Well, this matrix then is the matrix that has negative 2s along its diagonals plus a matrix that has all 1s. Okay, and this matrix here, if I call this A, this matrix here is actually uv transpose, where u and v are both the vector of all 1s. All right, so what that means is that this thing here is A plus uv transpose, and so the determinant of A plus uv transpose is, according to the matrix determinant lemma, the determinant of A, which is negative 16, times 1 plus the scalar v transpose A inverse u. And now A is a diagonal matrix, so it's actually kind of manageable to compute what A inverse is. So we'll have something like this for v transpose. A inverse has negative halves on its diagonal and zeros everywhere else. And then we'll have this 1, 1, 1, 1 vector here. So we get a negative 16 times 1 plus something. So here we'll get the matrix with all, or the vector with all negative halves as entries in one large column vector, and we're multiplying by this, so we're going to add up all the entries, we'll get negative 2, which gives us a total of 16. And I should double check here, so actually determinant of A is 16, not negative 16, so this turns out to be negative 16. Okay, so we can actually achieve negative 16. And you might think to yourself, this seemed like a miraculous thing, like where did I come up with this? Where did this come up from? And so the idea was, we had the matrix determinant lemma in this previous video, and so I happen to know then that this matrix with the negative 1s on the diagonal and the 1s everywhere else is going to have a non-zero determinant, right? And so it's going to be one of 16 or negative 16 or 8 or negative 8 by the argument that we said that determinant of A has to be in that set. I just didn't know which one of those is going to be. So we get negative 16. Okay, great. And so we can get negative 8 then, or positive 16 by multiplying any one of these rows by negative 1. So we can achieve that as well. And so the question is now, can you actually achieve 8 as a determinant? And it turns out the answer is yes. And one of the things that's going to help is a little bit of a modified version of the matrix determinant lemma. And so what I'm going to do is write out the matrix that actually gives you the determinant that you want. So it's going to be the matrix that we had before with negative 1 on the diagonal, negative 1s on the diagonals, and 1s everywhere else. But we're just going to make one small perturbation by changing this top left entry here from a negative 1 to a positive 1. Okay, and if you do that, and then also take the matrix where you multiply the first row by negative 1, you'll get these two remaining possible choices as possibilities as well. Okay, so you could actually compute what this determinant is and find out that it's one of positive or negative 8, but how would you come up with this idea like on your own? Well, you can start with the same setup that we had in the matrix determinant lemma where you have 1s everywhere here. But if this entry here is a positive 1, then we'd have a 0 here instead of a negative 2 like we had last time. So we'd have a 0, negative 2, negative 2, negative 2. And now you would hope to imply the matrix determinant lemma, which says the determinant of A plus UV transpose is the determinant of A times 1 plus V transpose A inverse U. The only problem with this is this lemma only works when A is invertible. And we have our UV transpose candidate right over here, where U and V were both the all ones vector. But this A is not invertible. So what do? So there's another version of this lemma that actually states that the determinant of A plus UV transpose is the determinant of A plus V transpose times the adjugate of A times U. And I'm not going to get into the details of this modification, but I'll say two things about it. One is that it works for all matrices A, square ones. It doesn't have to be invertible, so it sort of generalizes this matrix determinant lemma here. And secondly, this matrix here comes from minors of A. So what I suggest doing is actually try to figure out how to calculate the determinant of this whole thing using this, and take a look online for what the adjugate is to actually learn about it. Great, so that tells us then that our possibilities for the determinant of A are exactly the elements of this set from negative 16 to 16, including only the multiples of 8. So I hope you enjoyed today's video. If you did, definitely click the like button. And if you want to see more videos like this, definitely subscribe to the channel.